Hi, welcome to another 4AC work example 4.3D, which is found in your lecture notes. This is quite similar in format to 4.3C. A small factory has a 25 kilowatt resistive load and a 40 kVA inductive load. The inductive load have a lagging power factor of 0.6. If the supply is 850 volt and at 50 Hz, then we want to determine the capacitive element required to improve or to raise the power factor to 0.95. Alright, so again, let me draw out roughly the circuit. There is a resistive load of call it P1, 25 kilowatt, and an inductive load of 40 kVA with a power factor of 0.6, and this load is supplied by an AC supply of 850 volt with a frequency of 50 Hz. Now the first apparent power for this load is just 25 kilowatt. The second apparent power, S2, is actually the inductive load, but because it is at a power factor of 0.6, we have to determine the so-called the true power or real power and the reactive power for load 2, right? So this one is the apparent power 2, this is apparent power 1. So for this power factor is cos theta 2 is 0.6, therefore theta 2 is cosine inverse of 0.6, which gives me an angle of 53.13 degrees. Therefore, the real power for this particular load is S2 cosine theta 2. That gives me 40 cosine 53.13 degrees. Therefore, it's 24 kilowatt. The reactive power is then calculated from S2 sine of theta 2. That's equals to 40 sine 53.13 degrees. That's equals to 32 kVAR. So the apparent power due to the second load can be written as P2 plus JQ2 equals to 24 kilowatt plus J 32 kVAR. Therefore, the total apparent power for this load, if I want to put a dotted line here, the total apparent power can be added up, right? So we have S1, which is just 25 kilowatt plus 24 kilowatt plus J 32 kVAR. This gives me 49 kilowatt plus J 32 kVAR. So that is in rectangular format. I can convert it to polar format. That's 58.52 kVA, an angle of 33.1 degrees. That's the total apparent power as per this circuit. Now, if we now want to improve the overall power factor, right? This total apparent power has a power factor relating to 33.1 degrees. So it will help if I were to just draw a power triangle, then you can see what's happening. The real power P is 49 kilowatt. Okay, this remains as far as this system is concerned. Now it has a reactive power of currently of 32 kVAR, right, giving me a apparent power of 58.52 kVA, right, and this angle corresponds to 33.1 degrees. Okay, so this is the existing power triangle, but we want to improve the power factor, right? So the real power is still the same, so that is equals to 49 kilowatt, doesn't change. Huh? Now then, the new power factor, the one that we are trying to aim for, is 0.95, which means that the new angle must be cosine inverse of 0.95, which gives me an angle of 18.19 degrees. Right, 18.19 degrees. So in other words, I want to now create a new power triangle where this angle is just 18.19 degrees. So I will only need a Q T, that much, right? So I have to find a way to introduce a capacitor. To introduce a capacitor that will contribute this Q here, which we call QC, so that the final reactive power will become lower, right? So how do I know how much is that? The new reactive power is the original reactive power, which is this one, right? 32 kVAR, original minus the Q to be, or rather the reactive power to be provided by the capacitor that I'm going to add in. Right, minus this, which means that the so-called the reactive power to be provided by the capacitor is just Q minus QT. Now how do I calculate QT? Now QT can be calculated from the formula. So I calculate QT first. So okay, maybe I just running out of space, so I will move on to this new form. So I need to calculate QT. Now how do we calculate QT? QT can be calculated from PT, tangent inverse, tangent of the new angle, right? The original power, which is 49 kilowatt, tangent of the angle, which is 18.19 degrees. That gives me 16.1 kVAR. Right, then we go back to this formula that the reactive power to be contributed by the capacitor is then the original reactive power subtracted from the final reactive power, the new reactive power. So that's the original we calculated at 32 minus the new one is 16.1. So that's 15.9 kVAR. Alright, but we know that QC is actually the voltage, applied voltage square divided by the capacitive reactance. Therefore, the capacitive reactance Xc is equals to E squared over Qc. That's equals to the voltage, which is 850 square divided by 15.9 kVAr. That gives us a Xc of 45.44 ohms. The reactive capacitance, right? Reactance of the capacitor that I need to add in. But we know that Xc is equals to 1 over 2 pi Fc, which means this is equals to 45.44 ohms. Therefore, the capacitor that I need to add in must be equals to 1 upon 2 pi F. I replace with 50 Hertz, 45.44 ohms. That gives me a capacitance value of 70 microfarad. Alright, so in other words, in order to improve the power factor to 0.95, I need to add in a capacitor to the original circuit. Right, so if we were to look back at the original circuit, I need to introduce a capacitor here to improve this value, capacitor of 70 microfarad, so that my overall power factor is improved. Now, actually that's the answer required for this question, but just to make sure we understand what is happening to the whole thing, it's good to compare some values of the current, of the original current. Now the original current value which we can calculate actually, and then we compare with the new one, right? Now the original current, the original current IS can be calculated from the original apparent power divided by the applied voltage. So the original apparent power that we calculated was 58.52 kVA divided by 850 volt. So that is 68.85 ampere. Right, the new apparent power can be calculated from the square root of PT square plus QT mu square. So that's equals to square root of 49 square plus 16.1 square. That gives me an apparent power of 51.58 kVA. Therefore, the new current, supply current, is equals to the new apparent power divided by the voltage, which is equals to 51.58 kVA divided by 850 volt. That's only 60.68 ampere. Right, so this one, the power factor was cosine 33.1 degrees, whereas the new power factor is 0.95. Right, so a current drop, the maximum current drop when our power factor is improved. Right, Original power factor was cosine 33.1, which is 0.83, 0.837. So we improve it to 0.95, and the current dropped from 68.85 amps to 60.68 amps. Right, so this helps in cutting down energy loss in the circuits. Alright, that's all for this word example 4.3D. I hope you learned something. Thank you for watching.